All right, so we're in lecture 22 in section 4, advanced supervised classifiers. So in lecture 22, we talk about decision trees and backed version of decision trees. So this is the module 2 of this lecture. And in the module 1, we discussed the tree representation for a classifier. And in the module 2, we will review about a little bit information theorem, like this definition of entropy and information gain, and then how would you use those measures to split node to learn a tree representation. All right, so let's get started.
Okay, so now the question is, how do you learn that tree from the training data? So I'm going to give you only one really small piece about what a measurement people use to learn the tree, which is using the theorem from the information theorem. It's a very fundamental idea called entropy. So let's first see what's the issue of tree representation. So I'm trying to represent this Boolean function and A and B, or not A or and C, and this balanced tree can nicely represent this decisions. However, this function, this Boolean rule, can be also represented as the other tree. And it's essentially, which means the same type of projection, and from the x to the y, or to the a, b, c to the y. In this case, it corresponded to two different kinds of models, even though they perform the same type of prediction. And also, so that's the first issue, is the non-unique property. It's not unique. And the other is, so the how do you split, right? So let's just first see what is a bad split. So like we just did this exercise, we try to write on each node the positive and negative ratio the count representations. If we figure out, or we just come out some kind of plan, and every node, it gives me almost uniform distribution of the positive class and negative class. And it don't matter to where, and this tree, I just can't make a decision at all. And this is a bad split, which means why this is a bad split is because for every node, they're all give me this extremely uncertain information. What do I even mean extremely uncertain is all the distribution here of y and y positive and y negative are random. It's purely uniform. It's equivalent. Yes class and no class are equally likely on the node, which means we don't like this type of split node. We like the node is what? The node we prefer is those nodes are very unbalanced. Instead of being so balanced, we like the node to be really, really unbalanced, which means almost every node can give me almost always yes or always no. And those are the type of nodes we can call later is a pure node. Here is unpure node. We don't like unpure node. So how do you represent a node is pure versus impure? So this is give you an example, like for our famous tennis classification. If we use each of the features to split as the top node, these give me the first split is 6, 2, 3, 3. And this actually give me, for each of those, you can just count, right? This is like 5, 4. And this is like 6, 1. And so on and so forth. And you can actually tell this one, just from the intuitive feelings, this one is better. Just intuitively, this immediately create a node is already absolutely certain. All the other splits, they all have some kind of uncertainty involved in each of the children nodes. Okay, so this is our intuition. We want to reduce the amount of uncertainty. That's the whole intuition behind the decision trees. So to be able to figure out how to reduce uncertainty, let's first look how do you represent the amount of uncertainty first. So this just give you example is there are different kinds of probability distributions, right? And they are representing different amount of uncertainty. So let's think about roll a die. It's just observe the outcome of a rolling die, or observe the outcome of flipping a coin. Let's see the next. So in the end, so there's a famous definition called information. Oh, sure.
I had a question of previous slide.
Sure.
So how do you define this means bad split, in which the height of the tree is more, or means what kind?
So for now, it just means my node is so uncertain. So I try to figure out a split can reach the very certain nodes, decision nodes, as quickly as I can. That's my current intuition. I want to be certain as quickly as I can. So the question, did I answer your question? So the depths of the tree, all those are later. So let's just first figure out even just the first node split. How do you pick that node to split? All right. So again, we need to be able to represent the amount of uncertainty of a random variable in this case. So there's a very important definition called information, which is the minus log 2 px. So first, to understand this function, let's see what is log 2x. So this is just simplest function, right? Then what is minus log 2 px? Do I just flip it? Do a symmetric flip? What is minus log 2 px? What is the function for ix? What do function ix look like? Let me use px as x's. So, in fact, because of the axiom of px, it's bounded by 0, 1, right? What is minus log 2 px, it really looks just like this. It's a little bit difficult for me to write, to draw that, but just hugely. So as your p becomes smaller and smaller, the information got huge, got larger and larger. The intuition is, if the probability of an event happening is small, and it happens, that means the information is large. So that's the basic intuition. Let's just use example to show for the information for a coin flip. And the coin flip is totally uniform distributed. The I is equivalent to minus log 2, 1 over 2, right? Because it's uniform distributed. And the amount of information is 1. If for another event, another probability event is the roll the dice, which is also uniform distributed, the amount of information to observe one of the maybe 3 is I equals minus log 2, 1 over 6, which is 2.58, which means the information you observe for this 3, it's larger than the information you observe with a tail. Okay, so question about this? Sure.
How do people came up with log2?
It's actually bits. This actually from the coding theorem, which I don't want to talk about it because you use bits to represent it, right?
Okay.
How many bits do you use to represent this? How many bits do you use to represent that?
Okay.
That's actually the bits, the encodings, all from the encoding theorems. Yeah. All right. Okay, so now it's the entropy. So you actually already know the term of entropy, but we never even put the equations of entropy there. In fact, entropy is just expected Ix. It's expectation of the information, which you should remember what is expectation. It's really summation over all the possible values of that random variable, and then times the Ix as the specific measure you care. And then in summary, it just has the form is minus summation p log 2p. So let's use, maybe if there's 8 outcome, it's really just hx minus, and then you 1/8 is each of the uniform probability. There are 8 outcomes, right? Each one of them have the information is minus log 2, 1/8, and then together it gives you entropy, actually 3. All right, so for a discrete random variable, its entropy is upper bounded by log 2k. K is the cardinality of that random variable. So how many possible values this discrete random variable can have. So let's use Bernoulli variable to represent its distribution because there's only one parameter. We can represent h. This is actually p1, so this is hx, and this is the p head. So this is just, if your Bernoulli variable, the p head is 1/2, it means what? The p head is 1/2. This means a completely uniform distributed Bernoulli variable, right? The head versus the tail are completely equal to each other. And at that point, your entropy is maximized. And entropy is a function, it's a reverse bell shape. The more you're close to 1/2, the higher is the entropy. The more you're far apart from the uniform distribution, the lower is the entropy. Okay, so what does this mean? I already told you, I look for the points, each node, the pure, the better. If it's completely balanced, it's bad. It's completely unbalanced, it's good. So what does this tell me? The middle points are completely balanced, and the two sides are completely unbalanced. So in fact, I want to look for those children points. Entropy is extremely low. I want to look for those variables that can split my training samples and makes the node extremely lower in terms of the entropy. That's the whole intuition behind information gain. Question?
So in this case, I mean, we are only using the greedy approach, right? Like whatever is
Yes,
the best.
exactly. We only look one step ahead. We only look at one split. We don't look at 2 splits at all. We only look at, okay, what's the best current split, condition on my current situation. All right, so the whole idea is the more the probability distribution deviates from uniform distribution, the better, the lower the entropy. That's the better split we're looking for. Yeah, so this is almost the same. Okay, and also this also has the indication is those feature variables has a lot of possible values. We have bigger entropies. We have bigger entropies. And that will be why do I talk about it? It will be clear in the later slides. All right, so now let's compare. So this node 4 plus 4 minus. This is the node 8 plus 0 minus. And of course, I like this node, and the entropy of this node is very easily can be calculated. Yeah. All right, so now it's the definition of information gain. Information gain is essentially the reduction in the uncertainty of y by knowing a feature variable x. And it's calculated as entropy of parent minus the average entropy of all the children nodes. And in fact, if you think about it, because the entropy for a specific parent, let's just think for a fixed parent, because this is fixed, right? Entropy of a parent of that parent node, how the y plus and minus, it's fixed. So this is a fixed value. And here is the lower, the better. So the average entropy of children, I want to pick the feature with large information gain, which means which smaller average entropy, right? The smaller the better, which means on average, the lower the better, the more pure the children nodes. So I prefer average entropy of all the children nodes together to be smaller. Smaller the better. Again, what does entropy smaller mean? Entropy smaller means here and there. And on the two sides, not uniform distributed. Okay, so people just use information gain, higher information gain, and then pick that variable. So then how do you pick it? So essentially you just do this. You calculate information gain of the x1 variable after split with my y, and information gain of the x2 variable with the y, and information gain of the xm variable with the y. So it's exactly hy minus hy condition on different x. Whichever is the largest, that's the x you pick to split. Question about this? Sure. This is just one step. So why do you even need to calculate hy, right? That's your question. So currently, I'm only representing you as the first node, only the top node. But when you split later, you actually, they're actually here. So it's going to be clear in the later slides. All right, so it's actually a pretty complicated equation. So how do you calculate hy? So we already know that it's summation of all the possible values, p log p. And that's hy. And then what is hy conditional on x? It's actually two. It's first, you need to calculate hy conditional on a specific xj, that specific value from that feature. And then you use this p log p. And after you have this, and you need to take expectation of all the possible values of x variable, which gives another level of summation j because you have multiple of, yeah, so this is the condition on specific values of that x, and then you need to calculate the entropy, calculate the expectation by taking account what's the probability of each of specific pxj. And then this summation pxj then multiply that each conditional entropy. This is how you get the final conditional entropy. So I don't want to calculate it, but I want to give you a concrete example to show how to do this. So again, so this is the training data we're given. So how do I pick from x1 or x2? So first of all, I need to write the nodes, right? So this is my root nodes, and the root node should tell me the basic proportion of positive and negative. So what's the y portion in this root node? How do I write positive? How many positive and how many negative? So the last column is cons. It's just summation here. 5 positive. Yeah, it's 2 plus 2 plus 1, right? 5 positive, 5 negative. Okay, so this is the root node. If I use x1 to split, what do I get? If I use x1 to split, true or false, and then what type of node do I get? If I'm doing x1, it gives you, so this is the true, right? It gives you, give me 4, 0, right? 4 positive, 0 negative. And if for the not, it gives me 5, 1 positive, 5 negative. Okay, let's do the x2. Easy, so easy, right? For the true, for the yes, for the no, and then if I'm using x2, it gives me x2 is the truth, so it's 2, 5, right? 2 positive, 5 negative, and then if not, if x is false, what I get is 2 positive, 3 positive, 0 negative. Okay, so no calculation. Which one should I pick? Based on the intuition we just learned, which one should we pick? Which tree? Yes, very clearly. x1, right? Because you see the 4, 0 versus 3, 0. This is much more certain. 5, 1 versus 5, 2. This is much more certain. And intuitively, we pick x1. And this is your intuition, right? And then how to do the calculation. So let me just do a simple calculation. Really simple. All right, so so let's copy the so let's just copy one of the case here. So we have 5, 5 minus, and this is x1 here, right? Go to the truth, go to the false, and then go to the truth. We got 4 plus and 0 minus. Then if go to the false, we go to 1 positive and 5 negative. Okay, so and each node there actually represent y, right? Those numbers are actually representing y. So now let's see how to calculate H y condition on x1 equals to truth. If you can still remember the equation we just reviewed, entropy is minus summation of P log P, right? And that's for a specific x. It's minus the summation of P log P. And in this case, it's P yes or P no, right? So there are only two cases. Actually here, the P is y. Y equals to yes, condition on x1 equals to true, and then log P y equals to class, condition on, actually no, not class, it should be, there are actually two cases. It should be like this. X1 equals to true, class P y equals to minus x1 equals to true, log P y equals to minus x1 equals to true. Okay, so question about this. This is really just the entropy definition, right? To loop over all the possible values of the variable you're interested in. This case is Py, conditional on a specific x, condition on x1 equals to true, and then you just do P log P and loop over all the cases of that y. And we have only two cases, positive and negative, and yeah, I think it's correct. It's correct. So P positive in this case is 1, right? Which gives me, and P minus is 0. So it's really just 4 0 minus. And it's 1 log 1, and then so the first term is, this is 1 and this is log 1, and second term is, this is 0. And of course you can't, but yeah, no matter what it really is, this is 0. So what is this? 0. Yeah, of course, right, because this is a pure node. The more pure, because it's on two sides of that bell-shaped function, this gives me 0 entropy. And you can also do the same thing for the 1 and 1 plus and 5 minus. I'm not going to do it, which is pretty easy. And then you just do, so this is the HY condition on x1 equals to true, which is the 0. And this is the other 5 plus and y minus. And then the y condition x1 equals to true happens how many times? It's really about how many times the probability of x1 equals to true, right? The probability of x1 equals to true is 4 over 10. Then 4 over 10 over that entropy you just calculated. 6 over 10 is the other size you just calculated, which is, this is 4 over 10, and this is 6 over 10. This side is 4 over 10, and this side is 6 over 10. That's the reach proportion of how many points it equals, how many points x1 equals to true, how many samples x1 equals to false. And this is that portion, because this is expectation, right? So you have to multiply the entropy condition on truth times the probability of x1 equal to truth in the whole portion. That's how you get the final conditional entropy. And this is exactly how you calculate information gain. You just do hy minus hy conditional x, and then that's it. In fact, after this, you can implement decision tree, a simplest decision tree, very easily. It's actually very simple, right? For the discrete case, it's just a lot of counting plus the simple equation of expectation of entropy calculation. Okay, question about this? Yeah. All right. So will be a homework. You perform this calculation, hopefully to let you get a more concrete idea how to do this. And it's actually very easy to implement this through a program. All right. So so this is exactly the hy part, and then the whole calculation essentially is just this subtree. So x1 4/10 portion, false 6/10 portion, entropy of the children node, and then times the proportion of the left part of children, the right possibility of children. Together, you got that conditional entropy. And you can do the same thing on x2, and then you can perform. Then is for this specific is because there's only one possible split. It's from the root node, right? That's why you can just essentially only just compare the conditional entropy. But when you have many features, how to decide what's the next node even to split needs a lot of decision. Let's come back to this. So it's a little bit too much to come back. Yeah. Let's maybe later. There's more complex figure representing a more complex tree. So here there's only one level. So that's why you don't see this part as contributes much. But when so this is a summary. So let's actually maybe look at this. So after you split with the outlook, then how do you decide from here? Of course, this is an easier case because you have a certain node in the middle, and then how do you decide is from this node or this node to split? And then select what feature next. And at that time, you have to consider this node as the parent node, right? And then from this node, then you further split, consider other features to generate grandchildren nodes, right? And then how do you decide which children node, and then how to split the children node into grandchildren node? That's why the information gain has part of the HY, the H parent. In fact, it should be the H parent to be considered. Okay, questions? All right. Okay, so what's the caveat of decision trees? The number of possible values influence the information gain, which is exactly what we covered. Hx is upper bounded by log 2k. So that hy conditional whatever you reached so far, it's upper bounded. It's actually goes to hy conditional x, and it's maybe more easily. Let's do write this. It's log 2k. So it's kind of prefer the more possible values, the higher the gain, and the more likely is to form smaller but pure nodes. So it's always have a preference with those features has a lot of possible feature values. And then there are other purity measures, like not just the information gain. There's another very popular measure called Gini, and this has a very simple function. I hope you remember this function, p times 1 minus p. So what is this the function form of this p minus times 1 minus p. Let's just do very simple case. Even there's just p and then this p times 1 minus p. What does this function look like? This is simplest middle school or elementary school math, right? P times 1 minus p. P is the x-axis and y is p times 1 minus p. It's like this shape, right? It's exactly, you can convert it as p minus 1 over 2 quadratic, and the center is the 1 over 2 position, and which gives you 1 over 2, upper bounded by 1 over 4, and which carry the same shape as the entropy function, right? So of course you can tell, I mean, so even though on the surface they look so different from the information gain or entropy definition, but in fact it has similar bell shape, the reverse bell shape form. And you can do the calculation pretty easily, but that's really simple to derive. All right, so then the tree has an issue, famous issue called overfitting, because it's very flexible. And there's also, so it's just very unstable, because whenever you have this high variance property, and then there's a disadvantage coming in, then is the instability. So it's high variance model, small changes in training data will give you big changes of the tree model. And it also has the hierarchy structure, which means if there's errors on the top node, it's easily propagated into the lower nodes. And there are two different approaches people use to solve this instability or this overfitting, and it's one's called early stopping, the other is called cloning. Early stopping is just you don't grow to the full tree, you stop very early on based on some kind of measurements you defined. And the other type is you grow to the full tree and then you backtrack, prune those edges that you can use validation data to realize they are not as important as some other branches of nodes. So to summarize, the decision trees are nonlinear classifier. You can also for regression. It's really easy to use. It's really easy to explain. But the issue is because it's a purely greedy choice, right? There's also not unique solutions, and also very unstable. So it's just susceptible. So it's very easy prone to overfit, but there are actually a lot of strategies to avoid the overfitting, which is the next section. So to summarize, it uses greedy strategies to find partitions and pick out features as the nodes to split, and then it uses those kind of called purity measure, grounded from the information theorem. There are information gain or Gini, or there's also chi-square and cross entropy.
Great. So this is the end of this module. See you in next module.